Dear CATMEC members and team, first of all, I'm very thankful for giving me the chance for presenting some of our chemistry today in this final conference meeting. It's a pity that we could not meet together during the corona crisis issue, but I hope you can anyway enjoy the chemistry I'm going to present today. So in my group, actually we are devoted to develop new synthetic methods for making interesting molecules, especially with bioactive properties. We also really focus a lot of catalysis, especially in asymmetric catalysis, especially somehow designing new catalysts for anion-binding catalysis, but also we're interested in other type of methodologies like CH functionalization, rearrangement, and also lately photocatalysis. Today, I would like to present you two topics. The first of all, or the first one, based on the design of new catalysts for asymmetric catalysis, anion-binding catalysis in particular, and also design of new catalysts for photocatalysis. So let's start with the first part in the area of anion-binding catalysis. So let me introduce you a bit to this area. What is actually anion-binding catalysis? First of all, of course, we got inspired by nature, in which anion-binding processes are very important. For example, by binding to anions like chloride, it's possible to differentiate the potential. So by, for example, moving the chloride anion from one side to the other of a membrane by this kind of chloride channels. Also by binding anions, you can modify the structure and function of proteins. For example, this example with phosphate binding protein, BPV. And those, of course, this kind of type of interaction inspire the new area of anion-binding catalysis, which actually, based on this kind of interaction, what it does is to activate an ionic substrate or reagent, could be formed in situ already ionic in the media, which cannot react properly or not in the way we want with a nucleophile normally to get the final product. So then we use a catalyst that binds, or let's say recognize the anion, contra anion part, then leaving the reactivity that we want, or modulate the reactivity of the cationic part for the final reaction. So here we form a contact ion pair. In that case, if we have a chiral catalyst, we form a chiral contact ion pair, and we can transfer the chirality to the final product. So in this field of anion-binding catalysis, especially starting in organocatalysis, we were not the first. So of course, the pioneer work was made by Schreiner and Jacobsen, especially Jacobsen in asymmetric catalysis, in which actually the first and most of the cases uses thioureas, chiral thioureas, to have this kind of mechanism for the activation and chirality transfer. So you see one of the first examples here represented to form in situ, or he formed in situ the corresponding ionic substrate by acylation of this nitrogen, and then by binding to the contra anion, in that case a chloride with a chiral thiourea, form this contact ion pair, in which here the chiral or chirality of the catalyst can be transferred by making the new carbon-carbon bond in this final chiral compound. When we started our program, we knew that thioureas were able to bind anions. Let's say you can call it as receptor or acceptor, and then have this chirality transfer in different transformations. It was also known in 2008, different types of triazoles ion-binding receptors, which actually present a very high binding affinities. However, they were not explored in asymmetric catalysis or in catalysis in general. Therefore, we started our program in the one we want to combine these two areas, so catalysis with triazoles as hydrogen bond receptors, to make new type of catalysis. So we have preliminary results in what we saw that just not very polarized CH bonds, although we have the trick of using a polarized CH bond in a triazole, or a little bit polarized, we can actually bind anions, which was expected by the previous reports I told you as anion-binding receptors. And also we could affect catalysis with these kind of systems. We could not get crystals, but by help of some calculations made by Christian Lichtenfeld in Münster University, we found out that upon coordination to the chlorine, you got like almost coplanar situation. So you have really the chlorine in the middle. So we actually thought how to go into the chiral systems just by extending here the corresponding P substituents to make kind of helical structure. So it's not an helicene because here it's not all pi-conjugated. We have sigma bonds, it's more flexible, but the idea behind was actually to get this kind of helical structures. So basically, we found out that the best solution to get a more defined M or P helical structure is to have already in the middle of the molecule the chiral centers. This trans substitution normally would give actually one or the other helical structure preferentially. However, of course, because it's very flexible, we will have like an open system, and upon addition of the chlorine in the media, then we have like a template to form the helical structure in a high amounts. So our design also was a bit going farther from bidentate catalysts, which were or are still the most used in organocatalysis, like thioureas, squaramates, and silendiols, in which you have this kind of bidentate binding to fix the anion, and then you can have the reaction to the ionic, or let's say cationic part of the contact ion pair. In our design, we thought that it would be better to use multidentate catalyst, a structure that can fix better the anion, but also interact with the cation to get a more fixed and higher enantioselectivities. So we actually work with 4 triazoles. It seems to be the better choice. So 2 are normally not enough because you don't have the helical structure, although you have the central chirality here, and 6 is too flexible, and then you lose recognition affinities. We also wanted to have this kind of structures to develop new reactivity for important compounds. In that case, we focus on N-heterocycles, especially 6-member ring. So you can have, of course, here many drugs containing this kind of heterocycles, from aromatic to, of course, chiral systems, the ones we were more interested in. But however, you can see that this kind of N-heterocycles are very useful in pharma and also drug discovery. So for that reason, we focus on the first reaction, the Reiset reaction, which is actually kind of the aromatization of N-heterocycles by acylation form of this corresponding ion or ionic substrates, and then by adding a nucleophile, you form the new carbon-carbon bond. Embracing anion-binding catalysis, Professor Jacobsen some time ago also used thioureas to form here with this salt, the contact ion pair, chiral contact ion pair, and then obtain high enantioselectivities in the new compound you saw here. So based on this first report, we also use our naive idea to have this cavity in the center of the catalyst in the helical structure, with you combine the chlorine and then have this chirality transfer to the final product. Same mechanism. So this is the catalyst we found to be the best for that reaction. We didn't get as high as the enantioselectivities as the one reported by Jacobsen, so we got actually moderate, but we learn a lot with this model system. So we need heterosolvents to get high enantioselectivities, bulky groups at the acylyl-ketene acetals, here TBS for example, and also isopropyl or terbutyl to get also good performance, especially focus on the enantioselectivity. And also we need the trop group here at the acylation group to get not only high or higher enantioselectivities, but also sometimes even reactivity. So this seems that these groups here, actually in this position, not one closer or one farther, are very important to have interaction with the catalyst and then fix also the conformation or orientation to get the corresponding good enantioselectivity. However, although we could not get high enantioselectivities for this particular reaction, so my student Mercedes, that started this project, was very enthusiastic and just changed the position of the nitrogen from the isoquinoline group here to one position closer here to the quinolines and tried the reaction. So actually he was surprised almost in the first shot. He got a very high enantioselectivity, so 96% E. Here by changing completely or slightly the catalyst structure, so here we have the regioisomers in these triazoles, lower triazoles, then it's more symmetrical, so actually easier to prepare the catalyst and also get high enantioselectivities. Just by changing slightly the nitrogen position, we somehow give out the hint that this kind of catalyst really also recognizes the cation part, so in that case the quinolinium salt, and not only the chlorine contranion. Just for giving you some feeling of the scope of the reaction, So the aromatization of the quinolines using the Reiser reaction is very broad using our catalyst. So you see here, again, through this intermediate or ionic intermediate form in situ, we have the possibility to have substitution almost everywhere, electron withdrawing, electron rich. However, maybe we can focus in the position which actually does not work, or they don't work so well. Especially you have a substitution in the 3 position of the quinoline. We got reactivity, but lower enantioselectivity. In all the cases, most of the cases were 90 or more than 90% E. But here, probably, this is too congested, the addition of the nucleophile in that position, and we never see addition in the 4th position, which is also electrophilic. The no-go on this reaction is if you have something in the 8th position, probably it does not let the TROC group space to turn, to make a space to the nucleophile to add, and therefore no reactivity was observed. We also thought to continue our program to the more challenging pyridines. So although they are more simple, actually more simple sometimes implies more difficult to control. And that is the case because in most of the cases already described in the literature, you get actually more regioselectivity to the 4 addition. Especially with metal catalysis, you can control a bit the stereochemistry as well. But however you think about anion-binding catalysis, this is far away from the positive charged nitrogen, and normally you can expect lower enantioselectivities. So the product we wanted, it was the addition in the 2 position as well. And we were very happy to see that our catalytic system actually works very well in that case, getting very high selectivity or regioselectivity to this product, and also good enantioselectivity. So basically this is the best example, 98% EE. So instead of talking about all the scope here, this is only representative samples, maybe again focus on the positions which are more problematic. Again, if you have something in the 3 position. Again, hinting that we have kind of recognition, almost like enzyme, to the substrate and the catalyst, or between the catalyst and substrate. In that case, if you have a methyl group, a bit bulkier group, you can even invert the regioselectivity down. We get only the addition in the 4 position, a bit lower enantioselectivity, but still good, especially for quinolines. However, you have something intermediate in the side, you start getting a mixture. The addition in the 2 position, very high enantioselectivity can be observed. In the 4 position, as I commented, far away from the positive charge, so you don't see this effect of the contact ion pair is far away, you get lower enantioselectivity. However, if you now close the system, you can also think you may have different reactivity, you get completely, again, addition in the 2 position here. So we're very happy to see that with thioureas, this reaction was not regioselective and lower enantioselectivity was observed, but our catalyst was not another catalyst. In that case, it was really selective, and is, I think till now, the only one be able to get high enantioselectivity with the simple pyridines. So further, we also studied other kind of nucleophiles. You saw before it was always the acetyl represented here. So we actually check a bit in the Mayer scale, and we actually could also use phosphates, so also similar nucleophility like 10 in the Mayer scala. We could also identify other very useful nucleophiles that can also be enrolled here, getting high enantioselectivities. Well, this is just a very modification. 10 acetals are working also very well. We can also go to 10 allele compounds. In that case, we need the nucleophility a bit higher. So here, the methyl group, you will see in the scala, has maybe 8, 9 nucleophility described by this Mayer scale. So it's still possible to be used. If you go down to non-substituted allele system, then low yields are also obtained. We are now actually currently working on the extension of this chemistry, and we found out that unpol hydrazones can also be used very efficiently in this kind of reaction, and also the enolates, so conjugated system, to get very interesting compounds. However, I would like to tell you the last sample in this chemistry we are doing with our triazole-based anion-binding catalyst. Before, maybe to have a small summary, we saw that quinolines and pyridines are very good with our catalyst, getting very high enantioselectivities with different nucleophiles. I present today with the one with silene ketyl acetals, also with phosphate. As I told you, we get very high performance. However, they don't work very well with isoquinolines. On the other hand, isoquinolines work especially well with thioureas. And then if you have actually to get a new reactivity, probably I will suggest you to use thioureas or chiral thioureas when you have isoquinolines as substrates or reagents, but actually our catalyst if you have the other type of heterocycles. And now going to the last, as I told you, last example is in which we change the nitrogen for an oxygen. So we go to beryllium type salts. Those are more challenging than the other previous ones because here you cannot have a substituent to modulate the electronics and the steric properties close to the positive charge. Moreover, they have other disadvantages. They are a bit less stable or less reactive in that case to oxycarbanion ions because they are aromatic and also tend to open after addition of a nucleohide, and then you don't get a corresponding stereocenter. Therefore, to try to fix and get more reactivity and also, let's say, selectivity to get not only the addition, not the ring opening, we thought that our catalyst system for the anion binding will be very suitable. What is done in anion-binding catalysis with beryllium type salts? Actually, only two examples. The first described by Jacobsen, in which he used inter or intramolecular 5+2 cycloadditions using a dual catalysis system, so actually based on a covalent catalysis. In that case, this nitrogen formed the corresponding enamine and then the beryllium salt in situ, while the other chiral catalyst, in that case thiourea from Schreiner, just is used to eliminate or extract the leaving group here, again to form in situ the beryllium anion. So by having covalent and non-covalent catalysis, they could get very high enantioselectivities in these cycloadducts or bicycles shown here. The other example was made by Metzen, not so a few years ago, using chromelium anions by, again, the corresponding intermediate or ionic substrate was made by enolization with the base and tips triflate. And then upon addition of the catalyst, in that case acetyldiol, could get, and the nucleophile could get the corresponding product, however in low or very low enantioselectivities. So we thought here we could actually have a better performance. Having the similar approach as Metzen, we thought that our catalyst will be able to fix better in the transition state or intermediate the corresponding contact ion pair. So going a bit farther, not taking all the details of the optimization was a bit a long process. I show you here the best performance. So actually our catalyst is very robust. So compared to other thioureas we tried here as well. So we can already have it present in the first step. So the formation of the chromelium anion with the TBS triflate, pyridine as a base, and also heating 60 degrees. So it was not the composition at all. So then we cool down the temperature and then add the nucleophile, and final after the reaction adding an acid to recover the carbonyl group functionality. So here you see we use normally 1 mole%. This is quite low catalyst loading for this kind of chemistry. And maybe to go to this point, it was very interesting kind of optimization. So we start with TMS chloride because we know our catalyst, this triazole, tetratriazole system binds very well anions like chlorine. However, we got very low enantioselectivities and also the corresponding low yields. This can be explained because TMS chloride is not very good enolization or silylation reagent in that case. So probably the first step was not very efficient. When we changed to TMS triflate, we got higher yield and also higher enantioselectivities, or at least higher than before. But however, when we changed to something bulkier like TBS triflate, we got also better yields and enantioselectivities. All the first studies were made with 10 mole%. Our surprise was when we went down to 5 and 1 mole% of the catalyst, we got even a better enantioselectivity, which is normally not a kind of intuitive because higher amount or loading of the catalyst, normally you expect to have also better enantioselectivities. We could also even go to 0.1 mole% without losing our high performance and enantioselectivity. So remarkable low catalyst loading for this kind of chemistry. So in the scope, I also show you some representative examples. We got in all the cases very high enantioselectivities when we have the chromelium intermediates, a bit lower when we have the sulfur in that case, and probably the one which is more exciting for me is the case of the naked berylliums. So in that case, we don't have the stabilization of the other aromatic system as I said, normally tend to ring open, and we got very good chemoselectivity and also high enantioselectivity in all the cases we tried. So we were quite excited to get these results, probably very high performance to get this kind of very valuable heterocycle system. The question here, so I will not tell you further examples we are working on now, but of course more important is how this actually works. So we were thinking about or having this question for a long time, so we decided to study more in detail lately. So we initially proposed this kind of template by adding the chlorine to form this helical structure to be the active in the catalysis. So we studied the titration of our catalyst with tetrabutyl ammonium chloride to see if you see kind of helical reinforcement or reinforced helical structure in generation, which actually is what we see. So here maybe you don't see very well, but without any addition of chlorine, we see very small bands here, probably because, as I said before, there is very little of the helical structure in solution. You have no template at all. However, by adding the chlorine, you see an enhance or a decrease of these two bands, somehow indicating this kind of helical reinforced process, basically having more of the helical structure present in the media. We also studied by NMR the stoichiometry, in that case by jog plot. Probably now it's not the most typical or popular method to use, but because only gives you good performance when you have a one-to-one complex. But we see by using the chlorine source, we get very perfect one-to-one complexation. However, for triflate, when we use the corresponding salt, we see basically no binding. It was kind of surprising because the last example I told you, we got also very high enantioselectivities when we had triflate as a contraanion. Therefore, we also studied a bit NMR titrations to try to get the binding constant. Of course, with triflate, we could not do it because basically by NMR, we see no binding, but by chloride, we could actually get a good match. So we see here the displacement, especially of the two triazole systems, which are the ones that had to bind more strongly to the chlorine. We could also use by bind-fate program, we could get the binding constant for the one-to-one model around 560 molar minus 1, which was more or less corroborated by ITC titration studies. In that case, by this kind of low binding constant, we don't get a very nice S-shape in our ITC titration. But anyway, we could get a relatively accurate binding constant for the one-to-one complex, in that case a bit lower. So basically we can say we are around 500 molar minus 1 with this kind of system, which is still enough, although it's low, to get a good enantioselectivity transfer. So again, a bit summary, we can get nice reactivity with chlorine, triflate with different kind of substrates. Normally we expect to have this kind of open shape when we don't have a nucleophile, electrophile, and especially an anion as a template. So here I have a small video. It was calculated by the co-worker, in which we have a model system with the tetramethyl ammonium chloride to see how actually the conformation of the catalyst should look like. So here you see the open complex or catalyst, and here already with the complex one-to-one with this corresponding salt. So I have the video, I hope you can see here. So basically what we expected to have kind of helical structure, relatively flat, with the chlorine in the middle, and the substrate a bit outside. So basically blocking, if this will be the actual substrate, one of the sides, and then therefore seeing the high enantioselectivity we observe. So when we see here now the potential, we see very compact system. In the middle, we have the chlorine, therefore is red, so negative charge. And we also see other positions like the triazoles or the methoxy group here in the side chain, which can also interact potentially with the cationic part. So we have different sites for coordination with our catalyst. However, still was intriguing that why it does work also not only with chlorine, but also with triflate in the catalysis. So he also, so Darek, there was the guy studying the computational, the computational studies, also check by different kind of addition of different anionic complex section, or in that case, the complete ammonium salt as guest. And so that for the chlorine, we can get easily the complexation with 1. With 2, actually, in acetone, room temperature, which are the condition of the titration, probably is not very favorable. But however, when we change to something apolar, like in the catalytic conditions and low temperature, we see that both the 1, 1, and 1, 2 may be a bit less favorable, but still possible. Both these can be formed in situ. In the case of the triflate anion, which is, as I said, more puzzling, was the case that we get even 1 to 1, 1 to 2, 1 to 3 complex to be studied. In none of the cases in acetone, so the binding studies we do normally by NMR, any of these complexes should be formed. All positive energies varies, energy levels. However, when we change to toluene and -78, again, the reaction conditions, we now start seeing the possibility for the 1-to-1 complex, however, not the other ones. This probably is an artifact because you have other interaction or positive interaction between the salts themselves. So in that case, having a summary, we could see that we cannot always get valuable information for catalysis if we do the normal binding conditions or determination of the binding constant by NMR, like in acetone at room temperature. So as I said, triflates should not bind. Chloride, yes, so especially you can expect to have the 1-to-1 system, but when you change to toluene or ethers or something apolar, which are the typical solvents to get the contact ion pair, at low temperature, now triflate can be actually used as an anion for the template and the formation of the contact ion pair, and actually chlorine is even more strongly bounded, and then you get better probably fixation and performance. So why we cannot conduct in the same way both the anion binding studies and the catalysis? Normally is due to the solubility issues with the ammonium salts or chlorine sources we use for this kind of binding determination. Therefore, we need to use something like acetone or something more polar. And if we try to use toluene or ether, you cannot really guarantee a complete dissolution of all the salts. However, you can get a hint. Maybe you get at least negative energies for the binding, that this will be a good anion to use. If you get positive ones, probably the recommendation would be to first make some calculations to see if at low temperature and apolar solvent, you start getting a binding to the corresponding substrate. Finally, I want to show you also another video because we did some folding mechanism to see how our system actually binds the substrate, ionic substrate. Here only the first steps of the binding, because it takes actually quite a lot of time to get these calculations. So you see at the initial time are the 2 triazoles or CH triazoles, which actually takes or overtake the corresponding chlorine and the corresponding complex itself. With time, it goes to one arm of the catalyst, and kind of this other arm opens to be able for the cationic part, in this case the salt, ammonium salt, to go into the cavity, going up the system to one of the sides, as we observed in the final complex I showed you before. So you see it's actually going to basically one of the arm, the other arm of the catalyst kind of opens, give freedom for this displacement. And as I said, it's only the first part of the folding of the catalyst. We already have this situation, chlorine in this position, the ammonium salt of the cationic part already in one side, a bit up of the system. And now the last step, of course, is to close again. So this arm has to close again to form the helical structure I showed you before. So this is nice to see. So basically we know now that the 2 triazoles in the middle are responsible for the first caption of the ionic substrate via the anion, or ionic substrate via the anion, and the lower ones, because you have this electron poor system, are actually the ones participating in strong hydrogen bonding. So basically here you can now design new kind of systems by modulating these 2 parts of the catalyst. The last thing I want to tell you about this part is that we also studied the catalytic pathway using also calculations, DFT level, and so in that case it was AM1, because it's a very large system, but give us very important information here. So basically, we use, again, simplified system, this quinolinium salt and TMS methoxy silyl-ketene acetal as a substrate or reagent. So first we have a very weakened bonded system already having a kind of pi-pi interaction between the pyridine or pyridinium salt and one aromatic system of the catalyst when the nucleophile is already approaching. The most interesting part is the transition state in which we observe for the first time very interesting interactions. So basically the chlorine is not only served as a template for making the helical structure of the catalyst, but also breaches the nucleophile, in that case from the silyl-ketene acetal, here the alpha CH bonds from the oxygen, in that case here, from the methoxy group, the substrate, again by hydrogen bonding, and of course the catalyst. So putting all together, giving a determined orientation to finally get the new carbon-carbon bond in a very specific stereochemistry. So finally, already this weakly bonded system in which the chlorine is more weakly interacting with the catalyst, already approaching to the silicon of the silyl-ketene acetal to finally eliminate the TMS chloride and form the neutral desired product. So this kind of breaching or templating of the chloride anion we are now exploring in our group with different kind of nucleophile that can have this kind of CH bond interaction, or in that case, hydrogen bonding with the chlorine to get high enantioselectivities and also try to discover new reactivities. And with this, I would like to change gears to the next topic, which is the photocatalysis, especially visible light photocatalysis, in which we can have the energy from the sun, or at least from light, to get reactions to work. Interestingly, going from very energetic UV energy or UV light, by using visible light, we can be milder, so we can control better the reactivity, but also by excitation with light, we can also get very different kind of reactivity than the normal chemistry we do in the ground state. Also, photoredox catalysis using visible light is very rich because basically upon excitation of the photocatalyst, we can have different possibilities. It can act as a reductant or as an oxidant, and depending on with which reacts, so for example, with a donor or an acceptor, we can have a reductive quenching or oxidative quenching and get very broad variety of chemistry. Here I show you two different types of catalysts used basically photoredox catalysis nowadays, based on metal catalysts, especially ruthenium and iridium, although there are others like copper, and also some organocatalysis like very cheap eosine Y, and also fucosomic-based acridinium catalyst. Of course, we were more interested, at least what I will tell you today, we are using both systems depending on the reactivity we want to achieve. We were more interested lately in the development of new kind of catalysts based on mesetyl acridinium, or actually not mesetyl, but acridinium salts, which are known to be very good oxidants. On the other hand, with the metal systems, we can have different reactivity because they can use more widely as a reductant also and as an oxidant. However, the powerful of the oxidant system from the acridinium can reach you, for example, different reactivity that you cannot achieve with the other ones, and also are less expensive than iridium or ruthenium. So we started our chemistry in that area, trying to introduce new radical precursors, in that case, silicon or simple silanes, basically sp3 carbon silicon bonds, to get new reactions using these very simple reagents. We focus on acridinium salts, try to get this kind of coupling reactions, for example, with radical acceptors. Before we started in this area, it was also some kind of approaches in which carbon-silicon bonds were used as radical precursors, especially by Festenberg and Molander, using this kind of activated silicates. And then using iridium or ruthenium, they can do different kind of coupling reactions, even with the two metals to get, for example, cross-coupling reaction with other kind of derivatives. However, in that case, you really need these catechol groups to activate the silicon. Here is the radical that it will generate it, bonded to the silicon, and at the end you cannot regenerate the system or recover, and you have a lot of waste with the catechol. However, you have a very nice reactivity with these kind of systems. On the other hand, by using simple C lanes, it was the reported or the work reported by Curie. In that case, it's based on a formation of an iminion in the cited state, or this iminion can absorb light. Now it's able to break simple benzylic C lanes or alpha-2 heteroatom, and then form the corresponding radical that can add in this to this iminion anion. However, again, this is a bit limited, but only works with alpha-beta unsaturated aldehydes as a substrate. So we found out that using the commercial available Photocatalyst catalyst with this mesyl group here is actually able, under visible light using blue LEDs, to break the carbon-silicon bond from the radical and then be able to be trapped by these acceptors to get a new coupled carbon-carbon bond. So we have different acceptors, as you see here, normally with electron withdrawing groups. To be a better acceptor are normal olefins with very good yields in most of the cases. In that case, we get also with ring opening via some traces of ethanol as a stabilizer of the solvent we are using, the chloroform. But you see, we can actually have nice reactivity with this very simple system. We can also have not only benzylic positions, but also alpha-2 heteroatom, as you see here. So to nitrogen, oxygen, or even sulfur. In this last case, depends on the nucleophile, we can even get a second carbon-carbon bond by intramolecular cyclization with the aromatic ring. So we were very happy to see that simple C lanes can be actually used now as radical precursors to get interesting new carbon-carbon coupled products. We also studied a little bit how this mechanistic actually works. So we make the reaction with the deuterated compound, benzylic TMS compound, and we saw no incorporation, or actually in that case, a scrambling of the deuterium from the benzylic position to the final product in this position. We did this because under photocatalytic reaction, you can also expect to have in the benzylic position an oxidation and probably deprotonation, in that case, deuteration in this position. So also we wanted at the end to see where the proton should come here in the final product. So we also made the reaction using deuterated solvent. Again, we only observe incorporation of proton here, not deuterium. So the proton source is actually not the solvent. So finally, what we add is to dry chloroform, some drops of DCl in water, deuterated water, because we know that chloroform we were using is actually per analysis, so not dry. And also we know that with the time also could be decomposed to have some traces of ACl. In that case, we observe very good incorporation of the deuterium in this position, which actually gives the hint that we need traces of water or ACl in the solvent to get the final product. Interesting here, when you start adding a lot of water, you also stop the reaction. So actually you need only very traces, small traces of the water for the protonation step. So this is the mechanism we propose based on all the observations. So upon excitation of the acridinium salt, we now have a single electron transfer to the benzylic TMS compound. So forming the radical cation and later elimination of TMS cation, we form this radical. The presence of this radical was also determined by trapping with tempo to get this kind of adduct, what was detected by GCMS, or even by the detection of the, let's say, radical dimer also by GCMS. This radical, anyway, reacts in the presence of our acceptor to form this intermediate 8 with a radical in this position, which can have a back electron transfer to form the corresponding anion and recover the catalyst. Oxygen can also do this, so we do the reaction under air. Under argon conditions, the reaction also proceeds, but the yields are much lower, probably because this back electron transfer is not very efficient, and somehow the presence of oxygen helps to make a faster catalytic cycle. Anyway, when we have this anionic species, we need, of course, the final protonation to the product, and now we know this is coming from traces of ACl, especially, or traces of water in the system. So basically, that was the mechanism we proposed. So we actually wanted to extend this to carbon-silicon bonds using aromatic systems. So we used this substrate and similar conditions. However, with the Fukusumi catalyst, we only observed traces and not of the desylylation product, but the corresponding aldehyde. So that was, however, very interesting because the benzylic oxidation using organocatalysis using visible light were not very well described. So actually, even with this catalyst, it was possible to do it with electron-rich system, having electron donating groups. Other systems based in eosine, or other organocatalysts were actually used, for example, here, flavins. However, in all the cases, you need electron donating groups on the aromatic system, or even adding acid conditions or Lewis acids. Therefore, in that case, we start our program, try to develop new oxidants based on acridinium photocatalyst. So we explore a little bit the problems with this kind of systems. So it is known that the addition in the 9 position by a nucleophile is possible, how to say, quenching the corresponding photocatalytic activity. Also, that is in the ground state. After excitation, in the excited state, now a radical can also react in the 9 position, again, destroying the catalytic activity of the acridinium salts. So the trick was to introduce very bulky substituent in this position that was first made by Fukusumi, here the name, using this mesyl group, in which these methyl groups actually block the addition of the nucleophile or the radicals to the 9 position, and therefore having longer times of the active catalyst in the system. However, when we check to the kind of systems in the literature, we always see the formation or the preparation of the system having an aromatic group in the 9 position, probably because the synthesis is easier. So you just need the addition of an aromatic Grignard to the corresponding ketone here, and then treatment with an acid, stroke acid normally, to eliminate water and form directly the acridinium salt. However, we thought that based on our expertise in CH bond functionalization, we can have a different kind of group here to modulate the properties, but also the reactivity of these systems. So we base our design on the corresponding called oxidative UV type reaction with acridanes. In that case, we use benzoyl peroxide as the best oxidant for the system. Also, half of the molecule ends up in the product, so a bit more economic, atom economic than other cases. We use a copper system to be able to do the reaction at room temperature to activate the corresponding peroxide, and also a ligand to, enhance the reactivity of the copper, and then the reaction with the corresponding isonitrile. So as you know, so the UV reaction, normally you form an iminion in situ. If you talk about the oxidative UV type reaction, it means you don't have the reaction between an aldehyde and an anamine, but already a tertiary amine or secondary amine that you oxidize to form the kind of iminion intermediate. So you have a secondary amine, you normally go to bis amides. If you have a tertiary amine, you go to the corresponding imides. However, normally you always have this reaction in alpha to the nitrogen. In our case, we have a conjugated system, or you want to say a bit benzylic or dibenzylic CH bond, the one we oxidize. So a bit slightly different than the typical oxidative UV reaction. However, we should expect to get, again, this imide as a final product. So, of course, you have, under those conditions, a double oxidation to the corresponding cation in this benzylic position, which can react with the isocyanide as a nucleophile to form this intermediate. Also, in that case, by cleavage of the carbon, also oxygen-oxygen bond of the peroxide, you also form corresponding acid and the carboxylate, which can add as a nucleophile to this intermediate to form this kind of system C, which form a kind of type of MAM rearrangement to get the final imide product. So we were happy to see that we can have these kind of reactions with a very broad substitution of the acridinium salt. Also, we can have different groups on the nitrogen, making a different modulation of the properties. At that point was Mustafa, who actually took over the project and said, okay, this is the perfect candidate for further oxidation and get this new type of acridinium salts as photocatalyst. So he made a different variety of systems. So here's only a few examples with different substitution of the nitrogen, so methyl, benzyl, and phenyl, and compare to the Fukushima catalyst. So we check or we measure the corresponding oxidation or potentials. In most of the cases, well, in all the cases actually higher than the commercially available Fukushima catalyst, 2-4 volts, for example, for the N-protected nitrogen, 236, and even we got one example with methyl groups here to 2.5. All they have the maximum or the second maximum divisible light area, so actually could be used for the type of catalysis we wanted to use. The first test reaction to see the activity of this new type of acridinium salt was the one represented here to form intramolecular CH activation lactonization. Actually, without catalyst, you get a bit of reactivity. What we saw that especially with the N-methyl and N-phenyl acridinium salts, we get very high yields compared to the Fukushima. By the same time, 18 degrees, actually we have even the other substitution, always a better performance. So we're very happy to see that our system is, as expected, better oxidant and better catalyst for this kind of transformations. Also, we saw that going from the properties of the Fukushima catalyst, which is known to have a low quantum yield and also short half times because of the stability anyway, we observed that our best catalyst, in that case with the phenyl group here, increased the quantum yield, fluorescence, and also the half time significantly. So not only is giving better performance, but also the photophysical properties are also better. We see that it's not only for one reaction the case. In all the cases we try, especially for oxidation, as I said, which are acridinium the most valuable catalyst. Reduction are not very good, but still you can get reactivity. So we saw that our acridinium catalysts were more effective than the Fukushima catalyst. So for example, benzylic oxidation of alcohols, addition here for anethol, of methanol, and also the carbon halogen cleavage in the final case. So we see for the oxidations, N-phenyl catalyst was the best, but for the reduction was slightly better, the N-methyl substitution. So here you see the potential, so especially you need oxidation, the more oxidative catalysts are the one that works the better. So how this actually works, what is the difference? So we didn't see by calculations a very difference between the excited states. However, when we check the Frank-Codon energy diagram from both catalysts, we see by the Fukushima catalyst, we see a very small gap between the localized excited state in the singlet and the change transfer, which later decay to the non-productive triplet. However, you see, because it's very small, the gap, this can jump from one to the other. So basically what will happen is that we go through the change transfer to the unproductive excited species of this catalyst. On the other hand, to our new design catalysts have a huge gap between the localized excited state and the change transfer state singlet. Therefore, we don't actually lose the population of the active localized excited state, singlet state of the catalyst, and therefore we have better performance. So basically here we have a non-permitted change transfer state and therefore a more photoactive system. So this study was made in collaboration with two colleagues in Spain, José Alemán at Autónoma of Madrid, Raúl Pérez, before was in Madrid, now is at University of Valencia, who actually helped us to understand this, the performance of our system. So coming back to the project we had in mind, so we could not till now get the CH bond cleavage. Now we have different conditions to achieve this, but I want to tell you the story about the benzylic oxidation. So we saw that with the acridinium catalyst, we only see traces to the aldehyde. So when we change to the corresponding new design acridinium salts with this amido group, here with higher potential, we start to see full conversion and also even half conversion after only 2 hours. And we get selectively the aldehyde and none or only traces of the desylylation product. Very simple setup. This new photoreactor, a bit more strong than only one leg. And also we don't need any type of additive to get the product in good yields, I would say. So especially we were happy to see that simple toluene could be now oxidized. So here you see that's probably because of the potential of toluene, why the normal acridinium was not possible to oxidize the system. With our acridinium salt, now we can get very high yields or good yields to the aldehyde when we use under air, but in the closed vial. So we have excess of oxygen, or use open vial, then we get further oxidation and then quantitatively to the corresponding acid. So we can modulate the reactivity and stop in the aldehyde. We see that we change a little bit the conditions. So acetonitrile water, so 1% of water was the most convenient system for this kind of catalyst. So we can do the reaction also with alkylic change here to make ketones, but the more interesting are the aldehydes, which are the more complicated. So we see here we have different possibilities for the substitution. For example, here iodine, lower yield, but because probably the oxidation goes first to the iodine atom, we can have also electron-rich systems, functional groups which are normally not tolerated by the oxidation. Here the low yield does not imply the oxidation of the boron in the pinacolate system, but just no reactivity. So basically we recover the starting material, and also we can have heteroatoms or heterocycles to get the corresponding aldehyde in good yields. So maybe more interesting, the mechanism. So what we propose is the formation of, by a single electron transfer with a cited catalyst, a corresponding radical cation, which can easily now probably be deprotonated to form this radical, benzylic radical, so similar than before, then react with oxygens to form this peroxy radical, get protonated to the corresponding hydroperoxide, or maybe here, once after the single electron transfer, the one, not oxygen, but the one giving the back electron transfer to form the anionic species and then be protonated, and then decompose to the corresponding aldehyde. So we see that this is the intermediate because again, we can trap these two intermediates we saw before, or we can detect them by a mass. So for that reason, we actually convinced that this is the mechanism that takes place. So maybe again, why, just to see how easy it is to get this deprotonation to form the radical. So we make a competitive kinetic isotope studies with normal toluene and deuterated toluene, and we observe already a good or high kinetic isotope effect of 2.7, which implies or suggests that the deprotonation step probably is the most difficult or the rate determining step. Also, we made some calculations to see how actually this deprotonation might take place and where is located the positive charge in this radical cation intermediate we proposed. So only a few samples here. So this is the corresponding density difference, the depletion here between the radical cation and the neutral system. So in that case for toluene, we see, especially in the aromatic system, in the ipso and a para position, we have the positive charge more intense, but also in the benzylic position, maybe we see better here in the C7. Therefore, in that position is easily the deprotonation as we actually expected. In the case of the iodine, in the 4th position, as we expect here, is very low, the positive charge, and especially in the iodine is the localized charge. Therefore, most probably we had side reactions and low yields when we have this kind of iodo system. However, with bromine and chlorine, that is not the case, and we get the expected high reactivity. As expected also, the deprotonation is much more difficult in the neutral system than when we have the radical cation, and therefore, anyway, still we have a rate determining step because it's not simple to get this deprotonation to occur. For that reason, especially with the electron donating groups here, electron-rich group, we got problems to get the oxygenation, probably because again, we have side reactions like in the case of iodine system. And after these studies, we find out that by adding a base, like a pyridine base, we can get a better performance and probably favor the deprotonation, which is the rate determining without the base, and make the side reactions lower and get the final oxidation or the side oxidation product in better yields. So we are now working a bit further on the scope of this reaction, and I hope we can publish this very soon. So to this, I would like to finish my talk, summarize a bit what I told you today. So I talked first about the design of new catalysts for anion-binding applications, especially in enantioselective synthesis of some heterocycles. Then based in the Tetracis triazole system with different type of motifs for binding the cation and the anion, at the same time, and fixation of the orientation for the high enantioselectivity. On the other side, I show you also the design of a new organophotocatalyst based on acridinium salts, in which we have in the 9th position an imide group, which also favors the state or the population in the single electron state, excited state, which is the active state for the catalysis. I show you also a few applications, especially in oxidation reactions, to show that the potential of this new catalyst actually is much broader than what we expected at the beginning. And I hope next time we see, I can tell you more on the application of this catalyst. So with this, I would like to finish. Of course, thank you my co-workers, because they were actually an amazing team, which is able, I'm able to explain you all the chemistry because they work very hard. So you saw some of the faces during the talk. This is actually a bit older picture from last year in summer. This year we could not make a picture like that. So I hope next year also again, we're a bit more social and we can meet all together. So I also thank my collaborators, all the funding agencies, and of course you for your attention. So I know you cannot now ask no questions, but if you have any question about my talk, just please feel free to contact me and I will be very happy to talk to you about that. So with this, I stop and all the best and keep healthy.